So let's look a little bit more at this thermal and haline buoyancies, just to make sure that you understood the sign conventions, which are a little arbitrary for the net surface heat fluxes. This book uses flux going into the ocean as negative and coming out of the ocean as positive. Okay. Whereas before we had seen this map where we said upwelling is creating cold SSTs in these regions, and then atmosphere is trying to put heat into the ocean to warm those SSTs, and that results in the net heat uptake by the ocean. I like this convention better. And the western boundary currents move the heat from low latitudes into these mid latitudes, Kuroshio and the Gulf Stream, and the Agulhas, part of the Agulhas here, not so obvious in the Brazil Malvinas current, but East Australian current is also losing heat. Nonetheless, just remember that you make sure you know which way the heat flux is going, despite the sign. The latent heat taken from the ocean, obviously you can write it in terms of meters per year, as we saw LE times dm dt, which is comparable to something like condensation heating in the atmosphere and rain in meters per year or so. So we know that this is about 1 meter per year on average. We can compute the evaporation in similar numbers as well for comparison. What does latent heat flux and precipitation give us? Latent heat flux is basically evaporation, and precipitation is the net freshwater flux. So if we look at surface salinity, the regions which have high E minus P, so E is greater than P, give us high salinity. We already talked about the Atlantic being more saline than the Pacific, and you can see also the difference in the southern hemispheres. We will see that in this context there is actually salt being moved into this region, so you can see that the North Atlantic here is much more saline than similar latitudes in the Pacific, which we had seen before. This is in the order of 33 and less, whereas this is in the order of 35 and more. So obviously, combined with the temperatures, evaporation can produce deep waters here. Really cold winds come off the continent here and create massive buoyancy loss and heavy water formation in the Labrador Sea as well. There are other places like the Red Sea where bottom waters are formed because of the dry continental air creating buoyancy loss. There is also some bottom water formation in the Adriatic Sea, but those here it becomes part of the Mediterranean water that comes, Mediterranean intermediate water that comes out and cruises along and mixes with the rest of the thermohaline circulation. The Red Sea bottom water comes out of the Persian Gulf from the Red Sea and becomes mixed with the Persian Gulf water at a couple of 100 meters below the surface in the Arabian Sea, and then gets mixed with the Indian Ocean MOC. Okay, better to be aware of these in your head, kind of the locations of various buoyancy fluxes. There is the evaporation, there is the precipitation. We did a lot of dynamics, but we haven't really explained what selects these scales. That's a very complicated question, but you can see that despite all the trade winds and so on, large places of evaporation supply moisture to the narrow bands of rainfall. So the falling water as rain happens on much narrower regions, just like convection happens on narrow regions, and a lot of evaporation is needed to supply this meters of rain that falls every year. Similar things happen in the ocean. As we saw, there are very few spots where the sinking of water happens, and we'll see that the compensating upwelling and conversion of deep water to surface water happens over much larger regions. There are very nice studies that show how the scale selection happens, because remember here you're rising against gravity, so it's not just the gravity that can explain these different scales. Nonetheless, here is the E minus P showing there are regions of rain in the tropics, the ITCZ, the SPCZ, which we didn't talk about much, South Pacific Convergence Zone. There is actually also a South Atlantic Convergence Zone. There is negative E minus P regions also in mid-latitudes, as we know, related to the storm tracks and the eddy fluxes and so on and so forth. These determine the buoyancy fluxes as well, because the buoyancy fluxes have a thermal component. Now we are looking at this in a zonally averaged sense, meridional section, which is our favorite section always. So here is beta S, and there should be a beta, there should be a alpha T as well. No, sorry, this is just surface buoyancy in 10 to the minus 6 meters squared per second cube. Get used to that units. So when it is negative here, it's out of the ocean. When it's positive here, it's into the ocean. So this is the buoyancy flux, not just the net heat flux. So obviously in the deep tropics, ocean is gaining buoyancy because there is warming and rain. So light waters are being formed. In the mid-latitudes, we are evaporating and losing buoyancy. So there is buoyancy loss out of the ocean, and then there is a buoyancy gain again at the storm track level, and then small changes at higher latitudes. Out of that, you can see that the thermal buoyancy dominates in most of the regions, but there is positive haline buoyancy here, which means into the ocean, so heavy water formations, and there's a combination of cooling and salinity effects here. So the haline buoyancy is also into the ocean here. Okay, so it's just a kind of switching back and forth between E minus P, net heat flux, and the net buoyancy flux. Okay, that's all. Should be something familiar to you by the time you are done with this. My computer is not heating up anymore and not making any funny noise in the recording, I hope.